Well, let us start. Um, uh, we will discuss today electromagnetic radiation, and now I want to discuss only the questions related to physics and everything related to our organization of exam can be discussed later in Skype. There is a delay about 30 seconds between my speech and your video, so if you ask some questions, please remember that I will answer on it only in a few seconds, not immediately. You can ask your questions here in chat, and also you can ask them in Skype. But please ask only those questions which are related to the material of lecture. All other questions can be discussed later. Well, our today's topic is electromagnetic radiation, and we have discussed electric and magnetic fields on previous lecture. Mostly we deal with static fields, but today we are discussing radiation, which is time-dependent field, which is changing time field. So, what is electromagnetic wave? It can be imagined as a self-propagating transverse oscillation wave for electric and magnetic field. There are some important properties of this wave. First one is that this wave is transverse wave, which means the wait a second. So it means the electric and magnetic field are oscillating in a plane which is perpendicular to the vector of propagation direction. Another important property is that electric and magnetic fields always oscillate in phase. If we discuss a plane electromagnetic wave, then we can say that maximum of electric field and maximum of magnetic fields are at a given moment of time in the same point of space, and they all both are zero again in the same point of space. Since it is transverse wave, which can be directed in different directions, it can be polarized. We will discuss this property later. Now you can see that two pictures which illustrate this property of electromagnetic wave. So this one is a plane on linear polarized wave, and this one is circular polarized wave. So here the arrows represent the possible position of electric field vector in a given moment of time. Well, we'll discuss it a bit later, so now let us come to the next slide. The basic properties of electromagnetic waves can be mentioned as wavelength, frequency, and photon energy. And the speed of electromagnetic wave is equal to speed of light in the vacuum. It is very high. It is 300,000 kilometers per second. So for most of things which we deal with in our everyday life, this speed is so high that we cannot even see the time of light motion, of time which needs to light signal to pass from one place to another. But anyway, there are many experiments which proves that the speed is not infinite. It means some time is necessary for light to get from one point to another. And frequency is related to wavelength and speed of propagation by simple equation 1. So we can write it in this way, or we can say that speed equals to product of f and lambda. Well, next property is photon energy. So this is some concept which were developed in 20th century, the concept of quantum mechanics, and in this concept the light beam can be represented as a stream of quasi-particles. This is not particles in our everyday experience, where particles can be considered as a small sphere, for example. So this is a special type of quasi-particles because they don't have mass, but they can transfer energy. And we can say about photons as about portions of electromagnetic radiation. Anyway, it has some important property. Its energy is determined by frequency of radiation only, and if we have a high energetically stream of electromagnetic radiation, it doesn't mean that energy of each photon is high. The total energy of radiation is determined by number of photons and energy of each photon. So we can have very high energy of radiation, for example, in microwave oven, but the energy of each photon is not very high in this case. So once again, energy of photon is determined by frequency only, and it is given by equation 2. And there are different types of radiation depending on its photon energy. Let us discuss them. So here is electromagnetic spectrum. This word is used for different physical for different things. So spectrum can be considered as dependence of intensity on frequency. In other cases, the word spectrum is used just to say about the whole range of possible frequencies or possible wavelengths. And here is a picture explaining this meaning of word spectrum. So we can see the range of possible frequencies and possible wavelengths. Let us discuss it briefly. So the longest electromagnetic wavelength is restricted only by the size of universe. So it can be as long as you wish. But of course, in experiments we cannot discuss such a long wave. Need a permission to see. Tomorrow's lecture. Actually, there is no lecture tomorrow. Well, let's continue. So the longest wavelength which we deal in experiments in everyday life is about several kilometers in wavelength, and the shorter wavelength, the larger frequency and the larger ability to transfer some information, signal. So the waves with wavelengths about 1 meter, from 1 meter to a few centimeters, are used in radio connection in, for example, television, radio, signal transformation in mobile phones. So for all these purposes we use electromagnetic waves with the wavelength of about few meters to few centimeters. So these are called radio waves. The next spectral range is electromagnetic waves, which appears when we have some object at high temperature. So the waves irradiated by hot objects are called infrared. Hot but not very hot. So, they are called infrared, and they have their wavelength between a few millimeters and 1 micrometer. And below 1 micrometer there is a visible light, which is very important spectral range. It is very important for us because about more than 90% of information we obtain with our eyes. So all our being is based on our ability to see visible light. And you can see from these pictures that the wavelengths which we can sense with our eye lie between about 400 nanometers and about 700 nanometers, so in this interval between 400 to 700. So the shortest wavelength which can we see is sensed as a violet color, and the longest we interpret as red color. So the light which has the electromagnetic radiations which has wavelengths smaller than violet is called ultraviolet, and the light which has longer wavelengths is called infrared, longer than red. They are called infrared. So that's why this region of spectrum is called infrared, and that one is called ultraviolet. At the beginning of 20th century, everything which was shorter than visible light was considered as ultraviolet. But at the same time, a new type of radiation were found, which is X-rays and gamma rays. X-rays appears in a process of electron interacting with material. When electron is accelerated to high energy, it can then be it then interacts with atoms of a node and produces very highly energetical photons, which are called X-rays. And gamma rays are the radiation which are produced in nuclear reactors. Well, so this is the spectral range, and if we want to know what is the end on this side, what is the shortest wavelength of electromagnetic radiation, the answer is there is no limit actually, but to get higher frequency, to get shorter wavelengths, we need high energy, and this energy should be given to single particle. This can be produced, for example, in a particle accelerating device, like for example Large Hadron Collider or some other particle accelerator. So the photons with energy higher than gamma rays can also be produced, and there is no limit on this side of spectrum range. Well, let's go to the next slide. So here is a historical, short historical notice. I don't want to read all of this. You can do it yourself. You can stop the video and later, or you can get my presentation and read this page there. So here is a few words about invention of electromagnetic waves. It's by James Maxwell in the second half of 19th century. So he was the one who found equations of time-dependent electromagnetic field, and from these equations he was able to predict the existence of electromagnetic waves. He was the first one who added some term in this equation which allows existence of these waves. So the waves were predicted before they were found in experiment, and experiments were done in 1886 by physicist Henry Hertz. He have created an apparatus which allowed to generate and detect electromagnetic waves, and this was the beginning of radio wave period in our science. So radio for transmission of information was firstly used by Henry Hertz. Well, and in the end of 19th century, the George Wilhelm Röntgen found a new type of waves which is called X-rays, and later the new type of electromagnetic radiation were found in the rays produced by radioactive materials. So this type of rays were called gamma rays. Well, let us discuss some physical properties of electromagnetic waves, and we'll start with discussing properties of light waves. And you know there are some laws of so-called geometrical optics. These laws are valid when we deal with distances which are much larger than the wavelength of the wave. So in this case we can neglect the wave nature of light. We can consider the light as just a beam of something, without taking into account that it is a wave. So if we consider the light beam, we can find that it can be reflected and refracted. Refraction means that there are some materials which allow propagation of light beam. They are called transparent, and when the light beam comes through the border between two transparent materials, it can change its direction of propagation, and this change can be described by Snell's law of refraction. So this law says that ratio of sine of angle of incident angle, theta 1, and refraction angle, theta 2. So the ratio of sines of these angles is equal to ratio of so-called refractive indexes. And refractive index is the ratio of wave speed in the material to the wave speed in vacuum. Actually, inverse relation. So in vacuum the speed of light is the highest. So in some materials it can be lower than in vacuum, and the ratio of speed of light in vacuum to the speed of light in the material is called refractive index of the material. And Snell's law says that the ratio of sines is equal to ratio of refractive indices. It allows us to produce some type of optical devices. The simplest optical device is a lens, and it is a transmissive optical device. Another simple device can be a mirror, and the lens can focus disperse light beam in a spot, and this can be used for correction of vision. And there are different types of lenses: big convex, planar convex, so it's positive meniscus, negative, planar concave or biconcave lenses. There are different types shown here. And let us see what happens when the light beam goes through the lens. If we have a parallel light beam, then going through a biconvex lens, it will be converted into a spot, into a point which is called focal point. This phenomenon can be used for forming of image by biconvex lens. And the lens from the center of the lens and focal point is called focal distance, which is usually defined as f. And this focal distance is important property of a lens. In case of negative or divergent lens, for example, this one biconcave lens, there is no spot where the light beam will be converged, and anyway there is a focal point which can be considered as imaginary focus. So this is a point where the light beams crosses when it goes not the light beam, but it's the lines of light beam which diverge after going through the lens, they are crossed at a focal point. In this case, the focal distance is considered to be negative. Well, and there is a video in the description of this stream, and it will be in the description of this video on YouTube, which explains simple the formation of images in lenses. I recommend you to watch this video. Well, let's go to the next slide. And here is the equation which is called lens maker equation, which allows one to calculate the focal distance for a given lens. So you can see that it depends on radius of curvature for each surface of lens, and it depends on refractive index of lens. The larger refractive index, the stronger optical power, the smaller focal distance. Inverse focal distance of a lens is called its optical power, and the shorter focal length, the stronger change of direction of light beam produced by this lens. Refractive index for visible light for most of materials lies between 1 and 1.5. So there are only a few materials with higher refractive index, and that's why this factor is about 1/2 or smaller for most of glasses which is used in optics. And to increase the optical power, we need to use smaller radiuses of curvature, and the sign between these fractions is minus. It is because we take R with sign, and here is the rule how to determine this sign. I will not read it, you can do it yourselves. Well, here is the equation which allows us to find the parameters of images produced by lenses. If we have a positive lens, then its focal distance is positive, and the image produced by this lens can be real. It is not always real, it depends on the position of object. If object is located farther than F, the image is real, and you can see what it is. To produce this picture, we can use three beam direction. One beam which goes through the optical center of the lens, which is not refracted, so it goes straight to infinity. The beam which goes parallel to the optical axis of the lens, optical axis, is perpendicular to the plane of the lens. So this one, this light beam, it goes through focal point after refraction. So after this point, it goes here to focal point, and the beam which goes through the focal point after refraction will go parallel to the optical axis. All these three beams, they crosses at the point, at some point in a plane. This plane is the plane where real image is formed. If we put a screen in this plane, we can see the real image of object on the screen. If we don't put it anyway, the image is formed, but we don't see it. So it is formed independently of appearing screen in this plane. Well, next one is magnification. The magnification of single lens is not actually a well-defined parameter, because it depends on the distance on which the object is located. So if we want to define a linear magnification, we should say it is the ratio of size of object, of image formed by lens, to the size of object. So S2 is size of image, S1 is size of object. Image can be real or virtual, and anyway, in both cases we can say about magnification. For example, if we use a single lens to see small objects with eye, we'll usually put the object between focal between focal point and lens. So the image formed in this case is virtual image, but in our eye this becomes real image on retina, and we can see this image as real one. We can see this virtual image, and for us this the size of this image will be larger than the size of object. You can see that equation 6 contains f minus s1 inside. So s actually distances from object and from image, and if f equals to s1, so if object is in the focal point, then the size of image become infinite. Actually, if we use a single lens, it does not allow us to see as small objects as we want. It cannot allow us to see infinite small objects. Anyway, the magnification is restricted. And more powerful devices are microscope and telescope, which is used to see small objects or very distant objects. So the first one is telescope, which is used to see stars on sky, and it means the telescope is invented to see very far located objects. The simplest optical scheme of telescope contains of two lenses, and explanation of how it works can be given as follows. So the first lens produces the real image of distant object, of some object which is located far away. It is represented by this green arrow on the picture. So we have this real image of the object here in point 5. But then this real image is looked with the second lens, which is called eyepiece lens. So it is enlarged, a virtual image of this real image is produced here, which is represented with arrow 6, and this virtual image is looked with our eye. You might know that our eye has some optical power which allows us to see objects located on different distances from our eye, and the distance which can be seen clearly changes from about 25 centimeters to infinity. And the distance of about 25 centimeters is called the distance of the best vision. So if we don't use any lens and we want to see the smallest object, we will put it on a distance of about 25 centimeters. So the virtual image we produced by devices like telescope or microscope is considered as located on the distance of 25 centimeters from our eye. So we can see what we want so as it was on the distance of 25 centimeters. And the same scheme is used in microscope. The only difference is that objective lens in microscope has larger optical power, and eyepiece lens has smaller optical power. In case of telescope, the larger objective lens has smaller optical power, and eyepiece is higher. So again, we have an object. The objective lens produces real image, and then we see this real image with our eye using eyepiece lens, which enlarges real image and produces a virtual image for us. So eyepiece lens produces virtual image, and we can see it with our eye. So this is the scheme of the simplest scheme of optical microscope. One more property of light which can be considered as geometrical property is total internal reflection, which existence of this phenomenon follows from Snell's law of refraction, and this says that if we consider light going out from more optically dense material, for example, if light goes out from water to air, then Snell's law says that there is some critical angle. For this critical angle, the angle of refraction will equal 90 degrees. It means the refracted beam will go parallel to the surface. I'd like to remind you that the incident angle and the refracted angle are measured between the light beam and the perpendicular to the surface. So for example, here incident angle is 20 degrees and refracted angle is 27 degrees. And one more rule, that if light goes from the material with lower uh, lower refractive index, the angle of refraction is smaller than incident angle. But if it goes from more optically dense material, for example from water, which has refractive index 1.33, then the angle of refraction is larger than incidence angle. And for angle of about 60 degrees, the angle of refraction becomes equal to 90 degrees. If we have even larger angle of incidence, then there is no light beam in air. There is no light beam which can be refracted. The light doesn't go out from water. All the light which comes to the surface with incident angle larger than critical angle, for example, for water it is about 48.8 degrees. So all the light goes back to the water and doesn't go out. This phenomenon is used in so-called optical fiber. It is a long fiber which is made of glass, and since glass has higher refractive index than air, its large incident angles, there is a total internal reflection, and light doesn't go out from glass, from the fiberglass. So the whole electromagnetic energy is transferred through optical fiber without almost without energy losses. So this is widely used in internet connections, for example, connections between cities is mostly realized as the optical fiber connection. It allows to transmit very big amount of information in small time. And it also is used in medicine. Optical fibers are used in endoscopy as a source of light during endoscopy procedure. It is sometimes more useful than conventional source, electrical source, because it is quite thin, and it allows to transmit enough light, and it allows simple control of this light. So optical fiber is used in these devices too, and it is very widely used in telecommunications. Well, now let us discuss the construction and functions of our eye. And I'd like to tell you that there is one more video in the description of this video which describes the properties of human eye, so I recommend you to see this video too. And anyway, I'll explain something myself. So the eye optical system consists of cornea, optical lens, and retina is the sensor of light. So this optical system, which can be considered as convex lens, it produces a real image of what we can see. So everything we can see is is it appears as a real image on our retina. So our retina contains several types of light-sensitive cells. One type of these cells is called rod cells. They are very sensitive, and they can be triggered by a single photon. But they are not sensitive in terms of wavelengths. All the photons in visible light range can make the rod to produce a signal. And the signal is similar for every wavelengths. That's why vision by rods is color blink. So we cannot see colors with rods. And since rods are more sensitive than another type of cells called cones, that's why we can not see colors at low light conditions. For example, in twilight time we cannot see colors, and everything looks gray when the light is low, the power of light is low. Well, another type of cells, which is called cone cells, it requires significantly bright light, but it allows us to feel different colors. The color sensation is based on existence of three different types of cones. Here are two diagrams of spectral sensitivity to color. These are the same picture actually, but represented in different ways. This one is renormalized to unit intensity for each type of cells, and this one has the scale which is the same for every type of cone cells. So from the second diagram you can see that most sensitive cone cells are those who can see green light. So the maximum of sensitivity of this type of cells lies in green area of light. It is about 560 nanometers wavelength. Anyway, this type of cells can also see other type of lights, other wavelengths. Well, the second type of cells can see mostly red light. It is called red, can be called red cone cells, but you can see that it doesn't see only red. It feels yellow, it feels green. Its maximum of sensitivity lies at about 590 degrees, which is well, a signal from this type of light is interpreted as I think orange, because it contains it will contain a signal from red type cells and green type cells. And the third type of cone cells is blue cones. The sensitivity of this type cells is lower than for others, and its spectral range lies from violet to green. Since we have three types of cone cells, we actually can see only two-dimensional type of colors. If we had 4 or 5 types of cells, then we were able to see more colors. Our color sensation will be different. But since we have only 3 types, we can make an image of color sensation by using only 3 monochromatic light sources. And this is what is used in our displays. For example, the display you are using now contains 3 types of spots one produces red light, another one produces green light, and the next one produces blue light. And it is enough to make an image of all possible colors we can see. For example, brown color requires all these three types of cells to produce light. And if the intensity of these three types of color is in some special ratio, then we'll see so-called white light. Normally we sense the light as white when it is produced by a source like sun. So our sun produces a light which is very close to what we say white. We can see it as a little yellow, which is because atmosphere takes some, it actually it is not absorbed, it is scatter the blue light. That's why the blue light doesn't go directly at the same position where the sun appears on the sky. So some part of blue light goes to our eye from other areas of sky. And if we have light from both sky and sun in a sunny day, this light can be considered as ideal white. So it is a mix of light from sun and from sky. And this light can be imitated by our displays using three type of signals: red, blue, and green. We cannot actually find the difference between the white light produced by sun and sky and white light produced by display, because we have only three types of sensors. Well, let's discuss briefly distortion of light which can appear in our eye optical system. They are called hyperopia or myopia. In case of hyperopia or long sight vision, the focal point is located behind the retina, and we cannot see a sharp image of objects which are close to our eye. So actually this focal point changes its position with changes of optical power of eye length. And in case of normal eye, the optical power is enough to see both infinitely large objects and close to eye objects. In case of hyperopia, the person can see only objects which are infinitely large or large enough, but cannot see objects which are closer than, for example, 1 meter. That's why this person needs some correction for his eye to see close objects. In case of myopia, the focal point for infinitely long objects is located closer to the eye length than retina, and that's why there is no sharp image on retina again, and this person requires some corrective lens to see the objects which are at long distance. Well, now let us discuss one more property of light, which can be considered as wave property, because it cannot be described in terms of light beams only. It is a property which is called polarization. So I have told already that the light is a transverse wave it means the oscillation of electric vector E and magnetic vector B are in the plane which is perpendicular to the direction of light propagation, and in this plane there are infinite number of directions. If we choose only one direction in this plane, we will have oscillations of electric vector which are located in one plane with propagation direction. So the direction of oscillation and direction of propagation forms a plane in this case, and the wave in this case is called polarized. There are some materials which allows us to produce polarized waves. These materials are transparent for waves of some polarization, and they are opaque for the polarization in perpendicular direction. If the initial light is polarized at some angle to the axis of polarization material, then only a part of light will pass through the polaroid. So the polarization material can be called polaroid. And we can use the second polaroid to analyze polarization. If the planes of two polaroids are equal, then light goes through these two polaroids without less of power. But if polaroid and analyzer are at some angle, or if they are perpendicular, then the light, the only portion of light goes, and if they are perpendicular, no light goes through this system at all. This phenomenon is used in displays again. We have discussed that displays used our ability to see only three types of color waves, three types of wavelengths to produce color images. And another property of light which is used in displays is its ability to be polarized. So there are some type of material which are called leakage crystals, whose polarization plane can be changed using electric signal. And with this electric signal we can change the plane of polarization. That's why we can change the intensity of signal which goes through two polaroids. First one polarizes signal, the light. The second one can control its intensity. And this is used to control the brightness of spots on displays. Another application of the polarization is the medical one. It can be used for determining of concentrations of some substances. There are some substances, including sugar, which rotates the plane of polarization when light goes through them. And this can be used for measurement of concentration of sugar. So you can see this old style old style device to measure the concentration of sugar. The transparent tube. Actually, the tube itself can be not transparent, but it should have transparent basis. You can see the image of this tube here. When we put this tube inside this long metal tube, and we are able to see that polarized light which we can produce by polaroid here, it change its polarization plane. The plane is rotated, and if we put a second polaroid here, we'll see that light amplitude decreases due to rotation of polarization plane. By rotating this plane in opposite direction, we can do it using some crystal which rotates polarization plane, and by changing the width of this crystal, we can rotate it in opposite direction, and we'll be able to see again maximal intensity of light. And knowing the angle of rotation, we can determine the concentration of sugar in the solution, and some other substances can be measured in this way. And here is the modern device based on the same principle. You can see this small tube here, so the amount of liquid is much smaller, the precision is much higher, but the principle is the same. So this one is a device to measure the concentration of substances based on the phenomenon of rotation of polarization plane. Well, next property of light is dispersion. It is dependence of wave velocity on wave frequency or on wavelength. It can be seen by producing of rainbow by a prism, for example, and rainbow which appears in atmosphere after some weather conditions are produced by the same principle. So here are a few examples of rainbow and few pictures of rainbow, and this is the scheme which explains how the rainbow is produced. So the light beam goes in a spherical water droplet, then it is reflected, and during going inside the droplet, it is decomposed into colors, because different colors has different refraction index. Water has different refractive index for different colors. That's why light with different wavelengths goes out with different angles, and we can see these colored lines on sky due to this phenomenon. There are two rainbows here. The second one appears on the second order reflection. So when light doesn't go out here but is reflected again, and again, it goes out at some other angle. We can see the second rainbow sometime. Well, and what the dispersion, why the dispersion is important for optics? In most cases, it is a phenomenon which produces problems for optics, because if optical power of lens is different for different colors, then we have different focal lenses, and we have images for different colors at different distances. That's why image is not sharp, and that's why chromatic aberration, it is called chromatic aberration, which decreases ability of optical system. And to prevent this, there are some types of material used. The glass lenses are covered with some other materials which has different refractive index and different dependence of refractive index on frequency of light. That's why dispersion can be compensated, at least in part. Well, next phenomenon, next important wave phenomenon of light is interference, and this phenomenon can be described as the change in resultant intensity of two coherent light which are going to the same place. Actually, interference is a property of any wave process, and not only electromagnetic waves. And if there are two waves and they are in the same place. In many cases, we can see that the intensities are equal to sum of intensities of two waves. But if the phase difference between two waves remains always equal, those type of waves are called coherent. If they have constant phase difference, then the picture appears by interference of two waves is not just a sum of intensities produced by one wave. For example, if we have two slits in a diaphragm, we can see a set of strips on the screen instead of image of two slits. We are expecting to see only two white strips here, but we see a set of many strips of light and dark on the screen. Well, the interference can be described in terms of intensity. We should remember that intensity or power of light which goes through a given area this intensity is proportional to square of, for example, electric vector of light. And electric fields, by the principle of superposition, they are summed as vectors, and that's why total electric field E is given by equation 8. If you try to calculate intensity by the square of this E, we will have equation 9, so intensity equal to I1 plus I2 plus this interference term. So this phi is phase difference. If the waves are in phase, then phase difference equals 0, and cosine phi equals 1. We have intensity which is 2 times larger than what we had if we had no interference. So, for example, if I1 equals I2 and no interference, then I total equals 2 I1. But if there is interference, we can see that cosine phi gives us 1, this term gives us I1, and we have 2 extra I1, so total intensity is 4 I1. And this type of interference is called constructive interference. If the phase difference is equal to pi, cosine phi equals minus 1, and total intensity is 0. So the intensity is redistributed. In case of interference, some points obtain 0 power, some other point obtains double power. Now, in case of 0 power, we can speak about destructive interference. Well, and what is the application of interference? So interference is used in many scientific devices which are called interferometers to make very precise measurements of length and sometimes other parameters. Interference is responsible for appearance of colored images on a soap bubble. You can see this image, and you've seen it many times, and this is due to interference because the light reflected by outer and inner part of the bubble interfere. The two light beams interfere with each other, and the interference conditions depend on wavelengths. So for some colors, for some wavelengths, the conditions lead to constructive interference. These colors are increasing intensity, others decreasing intensity. We get this color image. Well, but the next phenomenon based on interference is diffraction. we can be considered as a bending of light around the corners of obstacle, and this diffraction can affect the ability of optical system. Due to diffraction, this ability is restricted, and one of the most important restriction is restriction of resolution of optical instrument. It is expressed by equation 10. So D is minimal distance between two points, which can be considered as different points. So in other words, G can be considered of diameter of spot of a point which is produced by optical system. In other words, we can say that G is minimal distance between two points which can be seen separately in optical microscope. And you can see that according to equation 10, which is called Abbe's equation, this distance between two points depends on wavelength lambda, depends on refractive index, and depends on convergent angle theta. In case of objects, actually it is divergent angle, so it is angle at which lights going from objects is absorbed by objective lens. To increase this angle, the objective lens should be put as close as possible to the visible object. That's why it should have very high optical power too. And anyway, even if we have highest theta, for highest theta equal 90 degrees, sine equals 1, we then can decrease D by increasing the refractive index. For this purpose, some liquid with higher refractive index is placed between the object and the objective lens. Those type of microscope is called immersive microscope. So in these microscopes there is a liquid between the object and the objective lens to decrease this D. And the last parameter which can be changed is wavelength, but you know we can see only wavelengths in interval from about 400 to about 700 nanometers, so we cannot make it shorter than blue light, 400 nanometers. And anyway, this type of resolution increase is not widely used because we lose information about colors of objects in this case. If we use only blue or violet light to see the objects, we will not see any colors. All the objects will be just monochromic, only blue. Well, so the next way we need to increase resolution of microscope, we could use to increase the resolution of microscope, is to use something different, not the light, but something different. And before we discuss it, let me mention that light wavelength is about 500 nanometers, or about 1/2 of micron. So the size of objects which can be seen in optical microscope is about 1 micron, or 1/2 of micron. Everything which is smaller than micron cannot be seen clearly in microscope. So for example, we can see cells, but we cannot see objects inside cells which are much smaller. We cannot see viruses, we cannot see many bacteria, so sometimes we can see them only as a point, but we cannot see any structures inside them. So there are many tasks we have for microscopy with high resolutions, but it cannot be achieved with optical microscopes. That's why we need some other type of microscope. And one of the first type of microscopy which was invented in 20th century, which is more powerful than optical microscope, is electron microscope. And even now it is the most powerful device in terms of resolution. So how it operates? It uses the beam of electrons instead of beam of wavelengths. For electrons, we don't have restriction by our vision ability. In case of light, we were able to use shorter wavelengths too, but there are no lenses for Röntgen light, for example, and there are no there are no refractive materials to produce lenses for shorter wavelengths. It is the second difficulty with using light for microscopy. That's why we need some other type of probe, and this probe can be electrons. Electrons can be accelerated to very high energies. That's why we can say that they have very short wavelengths. The same relation to of wavelengths to energy is valid for electrons too. So the higher energy, the shorter wavelengths. When I say about wavelengths of electrons, I mean the quantum wave properties. I will not discuss it longer, but the basic property of this quantum waves is that wavelength is smaller for high energies. And for electrons we can get very high energies of very small wavelengths. But to make images we need something which works as lens. And this object exists. It can be produced using electric field. If we use a electric scheme represented here, it will operate like an optical lens for electron beams. So it can focus electron beam. So if we have those lenses, we can create a microscope. It consists of electron gun, a node. So electron gun is some hot object which has high negative voltage. A node has high positive voltage and it attracts electrons to it. So electrons goes from electron gun and accelerated when they go to the node. Some of electrons are absorbed by the node, but if we have a hole in a node, then some part of electrons will go through this hole and we'll have highly energetical electron beam produced by electron gun. Then we need a so-called condensed lens which forces the electron beam to the specimen. When the electron beam goes to the specimen, some of electrons are reflected by atoms of specimen, some others go through. That's why the beam is now correlated with specimen density. After that, we need to enlarge the image because even if we have an image of specimen, it is as small as specimen now, and if we don't enlarge it, we are unable to see it. So we need to enlarge it. We use a few electrical lenses. So the first one is called aperture lens, and intermediate lenses, and the last one is called projector lens. After the projector lens, the enlarged image created by electron beam comes to fluorescent screen, some other detector of electrons, and it creates an image of object. Fluorescence screen produces visible light, and the image is enlarged. It can be seen then by optical, ocular, or can be taken picture by a digital camera. So many ways to see this image. And here is an image of real modern electron microscope. Um, in most cases, the image is directly given to the computer, so it is quite useful. But there are some disadvantages of electron microscopy. Um, it requires very high vacuum in tube where the specimens are placed, so we cannot put liquid specimens, for example. We cannot put any specimens which contains liquid. All liquid should be removed because it will produce some gas. Well, the width of specimens should be very small because at high widths we will be unable to see anything. The next restriction is that we cannot see many of biological objects because of they usually contains water. They cannot be done very very thin. And one more disadvantage is high cost of this device. And again, its advantages is extremely high resolution, and it can be combined with various other types of detection. Well, we have only 6 minutes. Well, another types of microscopy which is used in modern biological and medical studies are confocal microscopy. So in this case, we do not create image immediately. We create a light spot inside object and observe the signal using the same objective lens. So the same lens is used to produce a light spot and to observe the light on a detector. So at one moment we get the signal from one point only, and we need to scan the object. We need to move object or to move lights, all these devices relatively to object. What is the advantage? The advantage is that we can get higher resolution than in normal optical microscope. The image is to be formed on the computer only. There is no any screen where we can see image immediately. We need to scan the object, move it left and right, up and down. Well, but in the computer we obtain the image with higher resolution. We obtain actually we can obtain three-dimensional model of the object, because we can move the device not only left, right, up, down, but let's say farther and closer to the objective lens. So this is confocal microscopy, and also it is based on visible light. It allows us to obtain better images for many purposes sometimes. Next one is fluorescence microscopy. It is based on the same principle, but it uses some special substances which should be entered into the object, the fluorophores, and it uses different wavelengths for illuminating object and for absorbing light. For example, blue light can be used to illuminate the object to obtain fluorescence, and green light can be used for obtaining the signal. Well, next type of microscopy is scanning probe microscopy. One of this type, of this type is atomic force microscopy. In this case, a very thin needle moves along the surface of object, and it moves up and down due to the relief of the surface, and its position is determined by laser and um, detector of light. So again, computer allows us to form the image by this microscopy. It allows us to get also very high resolution compared to the one which can be obtained by electron microscopy, and in addition it does not require such strict restrictions to spacemans. Spacemans can be prepared much simpler for this type of microscopy than for electron microscopy. Well, next spectral range is ultraviolet. I will not read this text, you can do it yourself. Well, next type is ionization, and I'd like to tell you at least a few words about X-ray radiation. So X-rays appears when high energetically electrons comes to a node, to a metal electrode, and they interact with atoms of a node and makes the excitation of these atoms of very high energy. When atoms relax to its initial state, they emit very high energetical photons. Those photons are called X-rays. And X-rays are very transmittive. They can transmit through many materials, and they allow us to form images of, for example, bones inside our body. Well, here are a few words about gamma rays, and I think I have no time for laser, so let us stop at this moment since our time is over. You can read the information in my presentation, and I can answer now your question in Skype. So I stop the video. So goodbye.